Hey everybody, I'm Raphaël. I'm doing an internship here in Quandela, so for 5 months, so from February to July 2022. I'm in the theory team and my supervisor is Boris Bourdoncle, and I'm going to talk to you about the subject of my internship, which is randomness generation from single device. So basically the goal of the presentation is to give an overview of the subject of the internship. I'm going to explain some basic concerns and hassles mainly about randomness generation, and then I'm going to talk about the goal of the internship. First, I'm going to define what randomness generation means. So basically we have some process which is designed to generate some data. So it could be basically any data, but we usually consider binary numbers. And the point about this generation is that nobody can predict in advance what the outcome of the generation will be, a 0 or a 1. Actually, this seems pretty simple. We can maybe toss a coin several times and it will give us some random numbers. One tricky part about this definition is the nobody part. So to be sure that nobody with any knowledge or means or capabilities or whatever can predict the outcome in advance. To illustrate why this is a real problem in randomness generation, I'm going to show you some, let's say, some drawings, some small pictures. Imagine this little situation where you and some average person, maybe you made a bet, and so you need a random number to take some decision. So the person decides to roll dice, and you say, for example, if the result is 1, 2, or 3, you win, and otherwise the other person wins. Your opponent throws the dice, and you cannot tell in advance which outcome the dice will give. So you roll in and say you obtain a 5, so it's a random 5, since neither you nor the other person knows in advance the result would be a 5. Now let's consider this experiment again, but this time you're in front of an expert dice thrower. So this guy is really good. He can exactly obtain whatever number he wants. So in this case, you're not aware of it. So you play in this little experiment, and he treats you because for example, since the result is 5, he won, and you think it's a random result, but it's not. So this small cartoon illustrates a more fundamental problem, which is that it's hard to design a system, a device which produces data such that you can be sure that nobody can predict the result that will be generated by the system. You could tell yourself, for example, if I have a better model of the device, or maybe more accurate measurement tools or whatever, it would be maybe possible to predict in advance how my device works, and then predict in advance the result. So this is what we want to avoid. And so it's kind of really complicated. So actually one way to do this, say one good lead to generate random numbers or random data, is to use quantum mechanics, because one principle of quantum mechanics states that a special operation called the quantum measurements has to give a random result. So here we have, for example, some result M, which occurs with maybe some probability. So we can maybe deduce what this probability is and have a very good estimation of this, but we cannot beat this system, which means that even if we know the probability of which outcome, we cannot deduce in advance for each sample. We cannot deduce in advance which outcome will result. So this idea of using quantum mechanics to generate randomness has been long debated and used quite recently in some papers. So here we have our nice solution to the hassle that we presented in the beginning. And now we are left with another question, which is, how can we prove that a quantum measurement, so a probabilistic operation, is actually performed, such that nobody can deduce the result of the data generation? Well, for this, there are several solutions which I'm going to present. So the first one is called non-local games. It's a very well-known solution where you imagine that you have several players which cannot communicate and which have to so the players are asked questions and they have to give answers, and depending on the questions and the answers, they either win or lose the game. Now it has been showed that if the players are using a quantum system altogether and they perform quantum measurement on this system, they can achieve a better score than if they just give deterministic answers based on the question they're asked. So this is related to something called Bell inequalities, which are very well known now. So they have been used in some experiments where two devices are set up in a room, so they are near but they are non-communicating. Based on the score of this device, we know that the result of the measurement is random, and so experiments have been performed to produce randomness in this way. One thing about non-local games is that they have to use several players, so several devices, in order to implement an experiment. And you have to ensure that these devices are non-communicating. So it can be done in some ways, but this is generally the main problem of the implementations of non-local games. And also this is not very convenient because you cannot just have one device with you, which will generate random numbers. You necessarily have to have a setup with several devices. So the goal of my internship is to study other ways which only use one device to produce this random data. And so these ideas are quite recent, so 2021 and 2018, and are called shallow circuits and cryptographic protocols, with two reference papers which I've cited below. I'm not going to enter too much about the details, but the first one is based on cryptographic functions that are assumed to be hard to compute for any device. So just like classical cryptography today, but even resistant to quantum device. So the second idea to produce randomness with a single device is called shallow circuits. So the idea is to define some tasks which is massively parallelizable using quantum devices. So basically you can have tons of very small quantum devices next one to each other, and you can ask them to do some task and they will respond in a constant time regardless of how many devices are used. But if the devices are non-quantum, so just classical, then they necessarily have to take more and more time as their number increase, because they have to communicate all one with each other. And so this kind of time separation between quantum and classical devices allows to define a separation and to mitigate whether devices are quantum or classical. Now, the goal of my internship is first to read articles, kind of have a good idea of what these new ideas are and how we can use them to produce randomness. Another goal is to maybe, if I spot some things or if I have some ideas, I can try to improve some results about these papers. This is what I'm currently doing. And finally, one other task is to maybe estimate some resources which would be needed in Quandela, so with photonic device and linear optics, to implement such an experiment with single device. So this is a kind of approximate task, since these experiments will require a very big amount of resources. So maybe not for tomorrow, but one day maybe. And so that's it. Thanks for your attention. And if you're interested in discussing about randomness generation and non-locality or single device randomness generation, well, you can come and see me. I'll be happy to chat.